Welcome back. Now let's introduce some basic integration rules. I'm starting with some ones that shouldn't be too shocking. The indefinite integral of 0 is just a constant, and not a surprise, that's because the derivative of any constant is 0. If we were looking at the indefinite integral of a constant k, then that should be k times x plus our constant c. And again, that's reason for that is the derivative of that kx is k. That's kind of the idea for a lot of these integration rules. We can confirm them just by showing that the derivative of what our indefinite integral is gives us our integrand. So derivative of kx gives you k. That confirms that integration rule. 3 and 4, that's similar to rules that we had for derivatives, that we could take constants outside. So if you had a constant multiple, you could sort of leave it alone and deal with the function itself. Or if things could be split up into a sum or a difference, we could go term by term, adding or subtracting as we go. And that was the case whether we were doing the derivative of a function or if we're looking at the indefinite integral of a function. And here we've got one extra one. This one is sort of the reverse of the power rule, if you will. So we have the indefinite integral for x to the power of n. If we're looking for an antiderivative of that, that's x to the n plus 1 over n plus 1. With the side condition, of course, that n can't be negative 1, because if that were the case, you'd have divided by 0, and of course that's undefined. So we can now deal with basically any kind of polynomial or any sort of power of x kind of function, with the exception of 1 over x. We'll have to come back to that one at some later date. We can also deal with sums and differences and constant multiples, so now polynomials are within our grasp. The only one thing to notice here is we don't have anything talking about products or quotients. We're going to have to talk a little bit more about that later on. Now, as I said, if you wanted, you confirm all of those integration rules just by differentiating. So, for example, the one that we had, the one that was the reverse of the power rule, to show that this is the case, all I need to show is the derivative of x to the n plus 1 over n plus 1 is x to the n. If I can show that what I have is an antiderivative, then I'm good. So I'll start off with let n be not equal to 1, and let's suppose we wanted to find what the derivative was of x to the n plus 1 over n plus 1. So the n plus 1 in the denominator, that's of course a constant multiple, so I could really rephrase that as 1 over n plus 1 times x to the n plus 1. And now if I wanted to differentiate, I could say, well, constant multiple rule says the constant multiple can stay outside, and then power rule says that the power would come down and the power would get reduced by 1, and the n plus 1's cancel, and I'm left with x to the power of n. So since the derivative of x to the n plus 1 over n plus 1 is x to the n, then the indefinite integral of x to the n is x to the n plus 1 over n plus 1 plus constant c. Okay, so let's use these rules and find some indefinite integrals. Starting with the first one, x to the 5, indefinite integral of x to the 5 with respect to x. So for this, I'm just going to barrel on ahead and use that power rule, and for that one, it's adding 1 to the power, then dividing by the power. So 1/6 x to the 6th. Of course, don't forget our constant c. We have to be careful here. The little dx at the end is important. It's telling us we're integrating with respect to x. X is the variable for this. So if you're looking at b and noticing it looks quite similar, I'm looking at the indefinite integral of x to the 5 dt. This is not going to be x to the 6, because for this dt, that's telling me that t is my variable, in which case x to the power of 5, I would treat that as though it were just a constant. I would say then it's just the integrating of a constant rule. That is, if you integrate a constant, you get a constant times whatever the variable is. So this would be x to the 5 times t. Last one at the bottom, I've got 7x to the 13. And again, I'm going to use the fact that number one, I've got a constant multiple that I can take out front. So really that's 7 times indefinite integral of x to the 13. And then my power rule says that that would be adding 1 to the power and dividing by the power. And if I wanted to go one step further, I could make it look a little nicer and say x to the 14 over 2 plus our constant c. So sometimes I'll actually take the extra step of physically taking the constant out front, but just like we did with derivatives, some of the beginning differentiation rules, we've stopped splitting them up into little micro details as we get more confident, and same thing will happen with finding indefinite integrals. So let's do some more now. I have 3 terms, so I know for my indefinite integral it'll be just finding the indefinite integral of the first term minus indefinite integral of the second plus indefinite integral of the third, and it's dx for all of them. And now I'm just going to find the indefinite integral of all of these. So as I'm doing this, I'm going to do it and then revise what I'm doing. So if I were doing this each individually, I'd say, well, for 15x to the 4, it's 15x to the 5 plus a constant. And 33x squared, that would be 33x to the 3 divided by 3 plus another constant. And 2, integrating that, you have 2x plus another constant. But of course, if I had a constant from the first indefinite integral and a constant from the second and a constant from the third, I could combine them all together. I could just say, let's constant c be C1, C2, and C3 all added together. So I don't really need 3 different constants of integration here. I really am only going to need one of them. So keep that in mind, that although I'm going to start off splitting this up into 3 different little indefinite integrals, I don't really need 3 little constant of integration. And again, the splitting it up as I'm doing now, I'm doing that on purpose just because this is our first time doing an indefinite integral of something with a couple of terms. But you'll see for the very next one, I'm not going to do all the extra work that I'm doing right here. Same thing with the taking the constant out front. I'm doing this now because, again, we're still new to things. But as we do a little bit more work, we won't feel compelled to do all those little micro details. Okay, so next thing I would do is use my power rule and say, well, x to the 4 is x to the 5 over 5. X squared is x cubed over 3. And 2 is 2x. And of course, plus my constant c. And then the one thing I suppose I could do after that is just to clean things up a little bit as far as the couple of constants that I've got at the beginning. The 15x over 5, that's really 3x to the 5. And 33 divided by 3, that's 11. And there we go. There's our indefinite integral. But like I said, that's writing a lot more work than I intend to do. So as we start to get comfortable, I'm not going to split this up into 2 separate indefinite integrals. I just know that I'm going to find the indefinite integral of 10 over x cubed and of 3x to the 5, then add the 2 together. Similarly, same thing with constant multiples. I know that it's really just we're leaving the constant multiple alone, so I can skip the step of actually writing me taking the constant outside. The one thing I will have to do, though, for this one is to rephrase that 10 over x cubed. For me to use my power rule, I really need it to be rephrased as 10x to the negative 3, and then I feel a little bit better about using that power rule, because that was phrased in terms of indefinite integral of x to the n. So we really need the x to be on the same line that the 10 is. Okay, so now we'll just go and we'll leave our constant multiple alone. And now for our x to the negative 3, we add 1 to the power. Negative 3 plus 1 is negative 2, and divide by the power. Do the same thing for x to the 5. We'll leave that constant multiple alone. Add 1 to the power, and divide by the power. And then I can just clean that up a little bit and say that I've got negative 5 over x squared plus x6 over 2, and plus our constant c. Okay, last one. I'm going to do the same sort of thing. I'm going to have to rephrase these in terms of powers. So the x to the 1/2 is going to be replacing that square root of x. Cube root of x in the denominator is really x to the negative 1/3. And then away I go. I'm going to add 1 to the power. X to the 1/2 plus 1 is 3/2, then divide by the power. Negative 1/3 plus 1 is 2/3, then divide by the power. And constant c. And cleaning that up, I'll get 2x to the 3/2 over 3 plus 9x to the 2/3 over 2 plus our constant c. When I flipped and multiplied the 2/3 to make it 3/2, the 3 and the 3 from the 2/3 multiplied together to give me the 9. That's where the 9/2 was coming from. All right. We can come up with some indefinite integral rules. If we know our derivatives of trig functions, then we just have to rephrase it in reverse to get an indefinite integral rule. So we know the derivative of sine is cosine, so indefinite integral of cosine is sine. Or the derivative of negative cosine would be positive sine. So if you wanted to find the antiderivative of positive sine, it would be negative cosine plus a constant. And same thing for all the rest. They're all really coming from these derivative rules. The derivative of tangent is secant squared. The derivative of secant is secant times tangent. The derivative of negative cosecant would be positive cosecant cotangent. And the derivative of negative cotangent would be positive cosecant squared. So a couple of indefinite integrals to look at. So I'm going to go again term by term and leaving constant multiples out front. This one is all in terms of theta, so fortunately everybody's written in terms of theta. And away I go. I will leave that 5 alone. And I know that an antiderivative of cosecant cotangent is negative cosecant theta. And that's because the derivative of negative cosecant is positive cosecant, positive cotangent. Leave that 7 alone. Antiderivative of sine is negative cosine, and that's because the derivative of negative cosine is sine. And then plus 3 times sine. And that's because the derivative of sine is cosine. And then I'll just clean that up and write negative 5 cosecant theta plus 7 cosine theta plus 3 sine theta plus our constant c. And of course, you can also have things mixed and matched together. It doesn't have to be just trig functions. So here you can have polynomial functions and trig functions together. So, for example, starting with indefinite integral of 5, that's a constant, so it would be 5x. For 5x squared, that's power rule. Add 1 to the power and divide by the power. And then for cosecant squared, I know that negative cotangent has the derivative cosecant squared. And I know that the derivative of tangent is secant squared. And then that's pretty much that. There's not much in the realm of simplifying to do for this one. And there we go, we found our indefinite integral.